Hello students, my name is Shashank Shekhar. Today we will start the chapter D and F block. Okay, so before moving to D and F block, let us have a look at the structures of the D orbital. So these are the structures of D orbital. Okay, so if you see here, then they are the shapes of all the four D orbitals are same. Okay, this orbital, this, this, and this. They all have the same shape. But this one has a different shape. Okay, so this should be noted here that dz square has a different shape. Next, in addition to that, if you look here at the dxy, dxz, and dyz, then all of these orbitals are between the axes. Okay, so what do you mean by this? So let us just focus on this. So if you look here, the name is given that dxy. So first, what we have drawn the x-axis, and then we have drawn the y-axis. Now, in between the axis, we have the lobes. Okay, you can see this is first lobe, this is second lobe, this is third lobe, and this is fourth lobe. Similarly, we have drawn dxz. Okay, so we will draw the z-axis and the x-axis, and then we'll draw the lobes. But if you look here, for the case of dx square minus y square, the case is not the same. Now the lobes are on the axis, right? See, this lobe, the shaded lobe is on the x-axis, and this non-shaded lobe is on the y-axis. Okay, so this is the difference between these lobes, these three lobes, and these lobes. Now, what about dz square? So it is quite different. Okay, it is quite different. And you can see that there are only two lobes here. Only two lobes and a plane. This is a ring type structure. The one which you are looking here. This is a ring type structure, and there are two lobes which are oriented on the axis. Now, if I ask you about d orbital, that which of the d orbital is on the axis or along the axis, then you will say that these two sets are along the axis. Okay, these are along the axis. Whereas the remaining these three are between the axis. Okay. So we are studying about D and F block elements. So I think we should be aware about the D orbitals. The F orbitals are having a very diffuse shape, and we don't need to talk about them. So I have not mentioned the F orbitals here. Clear? Now, if you have seen the structures of this orbital earlier, then you must have seen positive and negative side. Okay, you must have seen positive and negative side rather than this shaded region. So it is depicting the same thing, that these two are in one phase, the shaded one, and these two are in the other phase. You can either take them both as positive and this both as negative, or the next case that can be possible is if you take this two as negative and these two as positive. So these are the two possibilities that you can take, and both of them will resemble the same thing. So basically, what I'm trying to say here is that the shaded region and the non-shaded region is done so that we can get the in phase and out phase. Means we can get two phases, right? We can get two phases of the two different set of lobes. Is this clear? Okay. Now, let us move to the next one. Now, one more very important thing, that out of these four orbitals, the dz square orbitals are the most capable of making the sigma bond. What is the reason behind it? Means it will result in the maximum overlap. Okay, it will result in the maximum overlap. So the reason behind is that apart from these four orbitals, right? Apart from these four orbitals, this dz square orbital has all the electron density, almost all the electron density on this two lobes, right? So you can see there are four lobes in each of this, but in this case we have only two lobes. Now, since the electron density is more, so whenever it makes this, you can say it makes this sigma orbital sigma bond. So you know, in sigma bond we require head-to-head on collision, right? So the dz square is oriented more along one axis rather than distributed along 4 lobes. Okay, and for that reason, it is capable of making sigma bond. So this is the important point. We will see this point. You must have seen this point in case of TVP. That for TVP, the DZ orbital which is involved. Okay, so you know the hybridization of TVP. It is sp3d. I think 3, 1, 4, and 5. Yeah, it was sp3d, and one d orbital is involved in that hybridization form for the TVP, and the one d orbital is dz square, and the reason behind that is because this dz square is more capable of forming the sigma bond. Is it clear? Okay, so we got an idea about this d orbitals. Now we will move to what are the d block and f block elements. Okay, what are the d block and f block elements? So for that, let us look at the periodic table. Okay, so if you just look at the periodic table, you will find that the D block of the periodic table contain the element of the group 3 to 12. Okay, they contain the element of the group 3 to 12 in which the d orbital are progressively filled. Okay, so again in D block element, the d orbital will progressively filled, and it is obvious, right? But if you talk about F block, then in that case 4f and 5 orbital are progressively filled. So whenever we talk about s orbital, so suppose we are saying that this is the s block element. Then in s block element, the s orbitals are filled. In p block element, the p orbitals are filled progressively. Similarly, in d block element, the d orbitals are filled. So if you talk about, we have 3d, 4d, and 5d. Three series we have. Okay, 3d series, 4d series, and 5d series. So in 3d series, 3d orbital is filled. In 4d series, 4d orbital is filled, and in 5d series, 5d orbital is filled. Similarly, for the case of f orbital, f block elements, we have 4f and 5f two possible, right? Because for 3d, for the third orbital, we don't have the possibility of f orbital, right? For the third shell, we don't have the possibility of f orbital. Clear? Okay. Now next. Now this is about 3d, 4d, and 5d series. But if you talk about the position of this F block elements, then they are placed in the bottom panel. Okay, so there are two panels here like this. We have our periodic table. Okay, so we have the periodic table in this fashion, right? If you remember, so this kind of shape is seen, and the bottom two panels, they are having our F block elements. Now the name transition element and inner transition element are often used to refer D and F blocks. This is very important. Okay. So instead of writing D block elements and F block elements, we write this as inner transition metals and transition metals. So transition metal is D1. Okay. So the D orbitals in which the D orbitals is filled, or the D block elements are also termed as transition element, and the F block elements are also termed as inner transition elements. Okay. F block elements are also termed as inner transitional elements. Next is the 3D block occupies the large middle section of the periodic table flanked by S and P block. So what does this mean? If you look at the periodic table, then on the both side we have S and P block. Okay, and in the middle we have you can say a middle section. With the rectangular middle section has the D block element. Now, if I talk about the type of D block elements, so mainly we have 3D, 4D, 5D, and 6D. Okay, we have 6D also, but mainly we talk about this three series, 3D, 4D, and 5D transition elements. Clear? Okay, so overall there are 4 rows of this D block elements, and for F block there are two blocks of F block elements, 2 rows of F block elements. So this is about the position of our D and F block for the D and F block element in the periodic table. Clear? Okay. Now, if we talk about the electronic configuration, then it goes like this. The general formula, it is n-1d 1 to 10, ns 1 to 10. So for all, so if we talk about, rather we talk about 3d, 4d, or 5d, then For 3D, the configuration will be what? According to this. So it will be n minus 1. 3 minus 1. Okay, so n minus 1 value is given 3. So that means n is equals to 4. Okay, 1 to 10. Now, next will be n 4 s 1. So this is for 3D element. This is for 3D elements. Next we have what? Next we have 4D. So if we talk about 4D elements, then it will be 5 minus 1 D, 1 to 10, and 5D, 5S, 1 to 2. Similarly, for 5D elements, what we have? We have 6 minus 1 D, 1 to 10, 6S, 1 to 2. So these are the four possible. These are the three general electronic configuration for 3D, 4D, and 5D. Similarly, if you want, you can write it for 6D also. Okay. Now, if you see here, then this one is representing what? This one is representing the number of electrons. So it can vary from 1 to 10. Okay, so this is number of electrons. Similarly, this is also, okay, so this is also number of electrons. Now it will vary depending upon the element. Different element will have different value of this. So it can go from 1 to 2, or I would say it can go from 0 to 2 also. Okay, it can go from 0 to 2 or 1 to 2 if you want. Okay. Now there is one exception, so that is the reason I was saying from 0 to 2. So let us keep that as exception. So this is the exception that is possible. That is for palladium. So if I talk about palladium, so it falls in the Ni, Pd, Pt. Okay, right? So what is the electronic configuration of this? So it is 4d10. So if I talk about outer electronic configuration, then it is 4d10 and 5s0. What is the reason behind it? Because you can see that if we have taken it in this way, we would have taken in this way, then it would be 4d8, 5s2. So these are the two possible electronic configuration for PD. Okay, and this should be the case. But since this is an exception, PD is an exception, we will have this kind of electronic configuration. So is this thing clear? And now here you can see very clearly that it is not between 5. So it is written here 5s should have 1 to 2 electrons, but it is having 0 electrons. Therefore, it is an exception. Okay, clear? Next, we can have more exceptions. Okay, we can have. So this is the exception to the generalization. Now next, let us look at some exceptions about the electronic configuration. So this is not the exception regarding the number of electrons or about the general configuration. We will now talk about those exceptions in which the normal filling of electrons is not taking place, and because of the Hund's maximum multiplicity, half filled and full filled orbital are preferred. Clear? So in that context, we have this. So Cr should have 3d5. So Cr should have 3d4 and 4s2. According to the normal above principle, 4s should be filled first, then 3d should be filled then later on. But if in this place we are filling, suppose in this case, okay, then in this case we can see that both of the orbitals, that is 3d and 4s, both are having half filled, and for this one we are having only one full filled. This is one full filled and this is two half filled. Okay. So for this reason, we can say that, okay, we will have 3D 5 4s1 rather than 3D 4 4s2. Next, we can have copper. So copper should have followed the above principle and formed this kind of electronic configuration. Like again, we will see this type. Why? Because this one has only one fulfilled orbital. But in this case, we have one half filled and one fulfilled. Clear? Okay. Now, so this is the electronic configuration of the first series. So first series refers to 3D elements. The scandium has an electronic configuration of 21, out of which 4s has 2 electrons and 3d has 1 electron. Again, for it goes on increasing the number of d electrons. See, 1 to 2, 2 to 3. But here, as I've said for chromium, there is an exception. Then we move to 5. So here should be 4, but it is 5. Then 5, 6, 7, 8. Then again, it should be 9, but it is 10. So these are the two exceptions for the normal filling. Clear? Okay. Now, talking about second series. So 1, 2, 2, again 4, 3 is missing here, right? 3 is missing here. So again, we have an exception here. Then 6, 1, 7, 1, 8, 1. And here is our exception, PD0. Okay? 5s0, 4d10. Now this is 1, this is 10. So you can see that except yttrium and zirconium, all the elements of second series have only one electron in the s orbital. Okay, so these are some exceptions you should remember. And CD also. So CD has fulfilled, so we don't have to worry about it. So talking about the third series and fourth series, so this is of what? This is of F block elements. This is also F block elements. So for F block elements, 1 to 2, 3, 4, 5, 6, 7. Now, instead of 8, we have 9 and 10, and then again 10. So 8 is missing here. Similarly, for fourth series, 1, 2, 3, 4, 5, 6, 7, 8. Again 9 is missing here. So these are the electronic configuration of 4F and 5F and 3D and 4D. So I will just mark the exceptions here with green pen. So this is one of the exception. These two are exceptions. In this, all of these are exceptions, right? Okay, so we are good to go with this electronic configuration of D block elements. Clear? Now we'll move to properties of transition elements. Okay, so again, the electronic configuration of the outer orbital of transition elements are Zn, Cd, Hg, and Cn is this. Okay, so this is the outer electronic configuration. But we have said that in D block element, the D orbitals are progressively filled. So I would just add one more thing to here, that if there is an unfilled D orbital in their oxidation state also, then also we will call it D block element. So if we take the oxidation state as Zn2 plus, suppose, then we will have N minus 1D, that is 3D8 and 4s2. So here D orbital is vacant, but in the oxidation state of +2 for zinc. So for that reason, it is D block element. Similarly, we can have Hg2 plus, we can have Cd2 plus and Cn2 plus. Therefore, they are fulfilled in the ground state and hence they are not considered as transition elements, right? They are not considered as transition elements. But their oxidized state, okay, Zn2 plus, Hg2 plus, they are considered as transition elements. Clear? Now, transition metal d orbital protrude to periphery of atom, more influenced by surrounding affect atoms surrounding them. An ion of a dn configuration having similar magnetic and electronic properties. So it is saying that it is being said that since the d are present on the periphery, means on the just on the boundary of our atomic you can say atom. Therefore, for that reason, it is affected by the surrounding. And if suppose 3 elements are having the same D configuration, suppose 3 elements are having D3 configuration, then they all will have the same electronic and magnetic property. So this is very important. Okay. So if we have suppose the same number of D orbital electrons, then they will have the same magnetic and electronic properties. Then this is clear. Okay. So if the number of d orbital electrons are same, then they will have the similar magnetic and electronic properties. But this is more pronounced if we are having the elements in the same horizontal row. Okay. So suppose if you are taking 3D elements, and so suppose I'm taking an example, right? Say we have, what are the 3D elements? So we have potassium, calcium, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel. So excluding these two, all these are 3D elements. Now if I talk about the electronic configuration of scandium, then it is 4s2 and 3d1. This is 4s2 and 3d2, and this is 4s2, 3d3. Okay. Now this is 4s2, 3d5. 4s2, 3d5. I think this was the exception. Okay, no, this was not the exception. So let me see. What was the electronic configuration of chromium? So was it the exception? Just try to remember it. Okay. So I think it was an exception. Here will be 4. So first of all, I'm writing it wrong. This is 4. Now, since it can be both half filled, so this will go in this fashion. Remove this all. So this is 1 set. This is 2 set. This is 3 set. Okay, so this is the electronic configuration of titanium, vanadium, and chromium. Suppose I am moving from Cr to Cr3 plus. Cr to Cr3 plus. Three electrons will be removed, and you will remove electron from the 4s and not from the 3d. This is very important. So whenever you do the ionization of this transition element, then you should never remove the electron from 3d. You will always remove it from 4s, because the outermost orbital will be the one that is giving the electron, and 4s will be the outermost, means it will be present on the most periphery, but instead it has the lower energy, but it is present on the outside. So this will this will release the electron first. 3 electrons are removed. So 1 from here and 3 from here. 1 from here and 2 from here. So that would result in 3d3. Okay. So Cr3 plus will have 4s0 and 3d3. Now you can see that vanadium also has the same number of d orbitals. See? 3 and 3 electrons. So these two will show similar magnetic and electronic property. Is it clear? Okay. So this was the point I was trying to make. So since these two are in the same horizontal group. So these two are in the same horizontal group. For that reason, we are seeing this similarity more pronounced rather than the vertical one. So suppose we are taking it for Karol Motiwala. So CRMO. So these two will also have the same number of d electrons, but The horizontal one will show the more pronounced effect. Clear? Now next. So contrast to the non-transition element. So this is not shown by the non-transition element. Okay, so this thing is not shown by the non-transition element. Now talking about some more properties, so they can display a variety of oxidation states. Okay, variety of oxidation state. We will see this variety. So you can have an oxidation state of +2, +3, +5. So vanadium can have +5, +2. Okay, so they can show a variety of oxidation state, and they can form color ions also. Okay, they can form colored ions also, and complex formation with variety of ligands. Next for properties, this so we'll study about this in coordination compound. And they will exhibit catalytic and paramagnetic behavior. So what is the reason behind paramagnetic behavior? The reason behind paramagnetic behavior is the presence of unpaired electron, and they have also catalytic properties. And in the recent times, rather than moving to the normal organic synthesis, if you have seen, the normal organic synthesis involved only organic elements. Like if you are saying about normal organic synthesis, suppose you are taking Finkelstein reaction or any other reaction, then that are the normal organic synthesis, and that does not require any metal ions. But metal ion do these reactions more accurately and more efficiently. Okay, so they are a very good catalyst. Clear? And why is that? What is the reason behind it? The reason is again the variety of oxidation state, means it can give and take electrons, right? It can give and take electrons because of the variety of oxidation state they can exhibit. Now due to that reason, it is having a very good catalytic property. Okay, so the catalyst is one which can donate and receive electron, right? So that is a very good catalyst. And since this is having a variety of oxidation state, so it can donate and receive electron, as it is stable in both of the electronic configuration or in the oxidation state. Clear? So the reason behind the catalytic property is the variation of oxidation state. So this is the question. Okay, so this is one question. The silver atom has completely filled d orbitals, that is 4d tail, in its ground state. How can you say that it is a transition element? So again, the reason will be same. So according to the modern periodic law, the element with penultimate energy shell has incomplete d orbital are called a transition element. Ag has complete 4d. It is written. Now silver has two oxidation state, +1 and +2. As I said, the oxidation state should also be considered. Clear? So in the +1 oxidation state, an electron of S is removed, and in the +2 oxidation state, electron from d orbital is removed. Thus, the d orbital has now become incomplete, so it is a transition element. So I made this point earlier also. Here the same thing is mentioned. So this was all about the D and F block elements. Now we will talk about the D and F block elements more in the next class. Okay, we will talk about the ionization energy and all. So this was for today's lecture. Thank you.